Thank you. So I will try to be as short as possible because of time. And basically, this talk is trying to summarize what has been done in the area of type 2 applied to intelligent control, which has been mainly my work, been done in the last years. Of course, there are other people doing this kind of work. So very quick, the idea is to show some of the concepts from interval type 2, general type 2 very quickly, and even intuitionistic fuzzy, which is related to interval type 2, as you may know, and some ideas of the applications. These are the people in my group. I skip this. Of course, many papers have been published in type 2, and I have also the privilege to have been publishing books and papers in this area. New Professor Zadeh for the first time in 1998 in Alaska in a conference of a WCCI conference, and somebody mentioned early, that was my aha moment, because I have read papers from him, but when I knew him, I knew this was the area that I would work in my future years. And this was in Berkeley here I think 2 years ago. And before starting very quickly, this area is very important. Right now, somebody was speaking about China just some few moments ago. Right now, China is the first place in number of papers in type 2, even in fuzzy, in general. USA numbers 2 and so on. You can find countries, even Mexico is there in 7th place, for the surprise of many, maybe. But we have the 31st countries there up to 2016, according to Web of Science. Also, surprisingly, from Web of Science, you can find the countries that are giving more funds to type 2. So you can see it's not critic to USA or something like that. But here you can see that China, Australia, Turkey, Mexico, even India are putting much more funds on type 2 research right now. This is from Web of Science, from the, you put in the papers the funding agencies, so this is from that. And in particular in type 2, of course, Professor Mendel is one of the missing people here. He's the top author in type 2, work from even 2000 from now. And in total, Fuzzy Logic has more than 74,000 publications according to Scopus. We can find the top country, again, is China, and USA, India, United Kingdom, Iran, and in type only 2,092 publications, and so on. This is according to Scopus. Not everything is indexed in Scopus, so these are like a subset of all the maybe publications in the world. But this is to give you an idea of the work that is being done in this area. This is only 500 miles south here. Is Tijuana in the top of Mexico, and it's close. We drive here 9 hours to be here, so it's not so far. And this is my group in Tijuana. Okay, so very quickly, interval type 2. The idea is that you have membership, but also secondary membership. So type 1 is just this part. Now you have a secondary membership, but in interval type 2, the secondary membership is constant to 1. So it's uniformly distributed, which in general type 2 is now again a fuzzy set. So you will have a fuzzy set, but in interval, which is a simpler case, you have a secondary membership uniformly valued at 1. So even this, in this case, you have an improvement over just type 1. And amazingly, this many don't remember that Professor Zadeh proposed the idea in 1975. He proposed the idea of type 2. Even if this was not continued until 2000 by Professor Mendel and then other people, he proposed the idea. So he's the father also of type 2, so he's our inspiration in that sense in this area. And the idea was in type 2 that the uncertainty can be modeled by giving this kind of membership functions, which are not single value memberships given to the fuzzy set, but in this case, interval membership is given to a fuzzy set. So for tall people, instead of just having this red simple triangular, now we have this shaded area which represents the footprint of uncertainty. And we have an upper membership function and a lower membership function to limit this footprint of uncertainty in this case. And so the member is an interval for when we fuzzify for a particular number, the height of the person, we have an interval membership instead of just one value. And of course, at the beginning, the problem was how to use this, and that was the seminal work of Professor Mendel proposing these switch points in the Carney-Mendel algorithm to just use two type 1s to approximate an interval type 2. But these two type 1 membership functions are not simple ones, are as shown here by one part of the upper and then switching to the lower one, and the other one opposite, one part of the lower one and then switching to the upper one. But you need to find these two switch points by the Carney-Mendel algorithm or then other approximations that were proposed later. So, but only two type 1s are to approximate an interval type 2. That's the beauty of this idea. And basically, this Carney-Mendel algorithm can converge in practical applications. 3 to 4 steps, iterative steps are needed to get a good approximation. So it's very quick, and in real world applications has been used for pattern recognition and so on. So even hardware implementation can improve speed. At the end, summarizing interval type 2, the architecture is similar to type 1. Just the new part is that a type reducer is needed to reduce a type 2 fuzzy set to a type 1 fuzzy set, and then the falsification is done to obtain a type 0 value or a number, precise value. So basically, the general idea of falsifying, then inference using fuzzy rules, then now the new thing, type reduction, and then you do the falsification. So the new block of type reduction was at the beginning the bottleneck for computing, because this iterative procedure needed here, the Carney-Mendel algorithm, was slow at the beginning. Now, because of new algorithms and because of new computers, it's very fast. And very quickly, just to illustrate, if we have fuzzy rules in this case, the difference with respect to type 1 will be that we need to find in lower and upper values of the antecedents of the rules. Then we propagate that to the outputs to find lower and upper. Then we aggregate the rules and we obtain a result. So basically, in summary, very quickly, two type 1s are sufficient to approximate type 2, but these two type 1s are special ones, are given by an approximating method, an iterative algorithm, which is the, I'm just moving here, this type reduction algorithm to find these two type 1s, and then we do identification. And this has been applied to many problems because it's very quick now. But now to the general or real type 2, which maybe we do not need to say general type 2 because they are really type 2, but they were generalized or generally set to express that we are using the idea. So basically here, a secondary membership, real fuzzy, here is used, fuzzy set. So we have like a fuzzy and then a fuzzy again. So it's type 2 in that sense. We have a primary membership function, then a secondary membership function to assign membership to the membership function. So we have a primary domain and a secondary domain, and so on, a primary membership function and a secondary membership function. So basically, this is to express the uncertainty over the values of the membership, which in type 1 are real numbers. So basically, here in this plane, we have the interval. But now in general type 2, we have another membership function to express the uncertainty over the values here, which in an interval type 2 was supposed to be uniform, so we didn't need the stir dimension. But this is now a complete case of a general type 2. And the operations are generalized union intersections, also proposed originally by Professor Zadeh, are in this form, and are called the meet and join operations. And so we have software for doing this. We have our own software developed for general type 2. So we represent with shades of or different tones of color the 3 dimensions, so to simplify this representation. So these are general type 2 membership functions for the singleton case, or non-singleton inputs can also be used. And we have our applications of general type 2 with this kind of software. And of course, this is a richer model because we have fuzzy over fuzzy. So we have representation of uncertainty by using fuzzy sets over the memberships in the primary membership function. Of course, computation is higher. At the beginning was prohibited to use almost this in the applications. Now it's getting to the real world because we are doing in parallel. We are using hardware FPGA and so on. And also algorithms are better. Also theoretically, we have been doing approximation, use less, in this case, alpha planes or vertical slices, which are the way to approximate this general type 2. In some sense, our idea is that, like in interval type 2, you use 2 type 1s to approximate. We believe that we could find 2 type 2s to approximate a general type 2, but this we need to find these special ones. But now we use many interval type 2s as alpha planes to approximate. Applications of this, you know, in control, Hagras from England, Coupland, and control, we also have work on that, signal processing, prediction, perceptual computing by the work of Mendel and others. So there are real applications of these in general type 2s. In the case, for example, from the work of Hagras, he did the application of these general type 2s for robot navigation. Actually, robot control navigation is very interesting because it's very uncertain if you use a real robot in an environment, and you have to follow an ideal path, but you have obstacles, and so there is uncertainty. And trajectories from a type 1 controller are very complicated because of these uncertainties environments. Interval type 2 is better, but general type 2 is even better. And the reason, our hypothesis is that it's like you are using many type 1 controllers because you have embedded in a general type 2 or even in an interval type 2 many type 1s. So embedded, you have like many type 1 controllers. Of course, you can do better. You can do more robust control, more stable control. And this has been verified in simulations and even in experimentally, like in this was for a real robot in a laboratory, of course. So interval type 2 assigns scripts for uncertainty. General type 2 assigns fuzzy sets for uncertainty. And interval type, of course, is simpler. General is more complex, but we are working on, I mean, we as the group of in type 2, not only in our university, but there has been many evidence type 2 outperforming type 1 in applications. Not all, of course, not all applications are like that, but in many applications, and this is important. Also, we have software for interval type 2, like similar to type 1 toolbox in MATLAB. So somebody interested in this, we can the software you like. Of course, only for research. This is not commercial, only for research. So you can implement your rules and so on, your interval type 2 membership functions, and then get results. Even for benchmark problems, you can see that type 2 can improve control over type 1. For example, this is for which is a very simple problem. You can have lower errors in this case in control for even that case. Another thing very quickly I want to say is that Intuitionistic is another area from fuzzy. Intuitionistic was proposed by Professor Atanasov in Bulgaria, and has been shown equivalent to interval type 2 with some conditions, of course. But the semantics are different because in type 1 you have like this membership for values of x. Then we have seen general membership over a membership for each value. But in Intuitionistic, what you do is you develop a membership function and then a non-membership function. So here, the belief is that for representing uncertainty in a problem, you can try to propose your membership function and then membership. And you assume that the sum of membership and non-membership is not 1. So the uncertainty is on this ignorance or this hesitation, they call it margin, which is the difference between this membership and non-membership with respect to 1. And so, of course, different problems can be solved by this. This is another form, another way of trying to represent uncertainty, but can be mathematically or theoretically can be shown to be equivalent, at least in equations, to interval type 2. But the application part is different because you can have difficulty in some cases, even if those two theories are equivalent, they may not be the same in practice for developing your application. So what we have done with the Professor Atanasov in group is assign secondary membership over, or secondary membership functions, membership and non-membership. So this is a combination of type 2 with intuitionistic. And this is like a new concept. I think Bob John is publishing a paper on this, similar to this, where an uncertainty of type 2 is embedded in the intuitionistic approach. So this is like a hybrid combination of intuitionistic and interval type 2, which can be also used in applications. Just to finish, because of time, let me show you this application system, which is similar to a helicopter. We have been working on it, and you know, this control of this kind of thing is very complex. You have many nonlinearities and also uncertainty. So it's interesting for us to apply these ideas to see if this modeling of uncertainty tools. And of course, you have to apply all the process. You have to develop your falsification, your rules, and then your defalsification processes. This is work with some researchers in Turkey. They wanted to do this application, and I am collaborating with them. So the rules were developed, the application, which are the membership functions, and then the falsification method. Initially, this is for the intuitionistic approach, the way that they falsify. This initially was done with intuitionistic. You know, here we have to define the membership and then non-membership, which are not complement to it. And also for the outputs, the rules for controlling the tail and the main rotors, which are the two rotors used in the helicopter. And this is the approach. So basically, you have two controllers, one for this rotor and one for the other one. And we can see first simulation, of course. So in this controlling problem, you have to follow a trajectory as closely as possible, which are these perfect lines. The controller is achieving this in the two rotors, which is very good. And this is that was simulation. This is for the real system, which is a laboratory. And you can also see that this is not so perfect experimentally as in simulation, but this is good also. So this is an actual good result, even using only intuitionistic. Now they are doing in type 2, and then the combination will be done. This is an ongoing work, but right now, even with this, we can outperform classical PID control with intuitionistic fuzzy rules and control. And so, just to conclude, we can say that type 2 can outperform in the case of control, like we have seen many papers from us, I mean, in our group and groups. And hybrid helps. I'm not talking nothing here about that, but we need to use meta-heuristic or optimization methods to optimize the controllers or the fuzzy controllers. Because, of course, if we do this manually, this is not easily done. So the results, so we need to optimize using genetic algorithms, particle sum, or any other method that can optimize the fuzzy system so that the fuzzy system can give the better results. And for type 2, it's even more complicated because you have more parameters. So we need to use this. And also neurofuzzy, type 2 fuzzy neural approaches are interesting. So we are also working on that. Intuitionistic type 2 is another area. So this can be found in many publications of us and other research groups in the world. So thank you.
In support of this research, because of course the very fact that we outperform is kind of no big deal in general, because of course you have additional parameters every time you can do a better optimization. But the good news is that many papers of Dr. Castillo and others, it was shown that with statistical criteria like AIC and BIC, indeed, the improvement goes way beyond this just random addition of additional parameters. So this is often a drastic, and not always, but in many cases, it's indeed a drastic improvement. So I would welcome everybody to look at.
In these rule-based systems, you have plenty of AND operators.
Yeah.
What kind of AND is that?
Yeah, we usually use mean or product right now. New researcher that is new in our group, we will do with him, we use parametric operators to see also an improvement can be done by not using only the simple operators in and OR. So we will.
You can have adjustable ANDness and go in.
Yeah, we can adjust to the problem because right now parameters in memory functions, but not in the operators.
Yeah.
And we will not want to do that.
Okay, thank you.
Was another question?
All right. The lady.
Okay, so you mentioned about you use an FPGA for implementation of your fuzzy algorithms.
Yeah.
Since you showed all your MATLAB simulation stuff, so do you have publications, or when you use FPGA, which was a hardware implementation, does that show better performance, or?
Actually, the performance usually is not as good as in simulation, but if the losing efficiency is not big, for the application is sufficient. So you will have to see if this decrease is not that bad, and so but you want to have quick response. For example, in image recognition, in software it was taking, and so they implemented in hardware, and it was very fast. Not as good, but you need quick response for real time. Yeah. Okay.
Yes. Thank you very much. All right.
Okay. Thank you.